All right, welcome back. In a previous video, we talked about translational velocity, rotational velocity, or angular velocity. We talked about translational acceleration, angular acceleration. We want to start talking about how they relate to each other. So let's begin this way. We're going to look at position or distances in a translational case and then compare that to a distance in an angular case or a rotational case. So we start off with the sector of a circle. So here's a piece of a circle, think of it as a piece of a pie, and we've got two radii, both of length r here, and they're separated by some angle theta. Then the crust out here at the edge of the pie has a length s, right? And so that if I was eating that edge of the pie, I would eat a length s of that crust. And s is equal to r times theta. So we learned that in a geometry class some time ago, right? We should have learned that at any rate. So now what we want to do is we want to think a little bit about translating across that through some time period. How fast am I moving? That would be a linear speed, or what's referred to as a tangential velocity, and we'll get to that more in a second. So first off, we need to make a couple of definitions of terms. First off, the period. The period, which I'm going to label with a capital T, is the time for one full rotation. So in our wheel here, if I start off there at 0 degrees, or the positive x-axis, and I go around, and it takes, let's say, 1 second to go around, then the period of rotation is 1 second. If I go a little faster, the period of rotation might be less than 1 second, let's say half a second. Or if I go slower, okay, that's not going to work. I have to give a little bit more oomph, right? So that was about 3 seconds. So the period of rotation would be 3 seconds, right? So the time for one full rotation, which is going through an angle of 2 pi radians, that was the period t. 1 second, half a second, 3 seconds, whatever that case might be. Another value that we've talked about in the past, not in these videos, but you've seen in previous material, would be the frequency of the rotation. Frequency is the number of rotations per unit time, generally the second, right? So 20 radians per second, not radians, rotations per second, oftentimes per minute. 20 RPMs is 20 rotations per minute. But we're going to mostly stick with seconds, but not always. You'll see problems where we look at rotations per minute. The frequency we designate with the letter F. Okay, so F is the frequency. That's the number of rotations per unit time. But there's a relationship between the frequency and the period. Let's think about it now. The period is the amount of time per one rotation, and the frequency is the number of rotations per unit time. So it turns out that relationship is an inverse one. The frequency is equal to 1 over the period. So if I had a period of, let's say, 5 seconds, I would have 1 over 5 seconds. That would be 1/5, right? 1 over 5 seconds would be 1/5 per second. But that means that there are 5 rotations in every second. So they're the inverses. So the period is 5 seconds, 1/5 of a second. Wait. Let's get back to this. The period is 5 seconds, 1/5 of a rotation per second. So the frequency is 1/5 of the rotation in every second. So they're an inverse relationship to each other, right? Frequency and then period, inverse relationship to each other. All right, so the angular velocity is the number of radians per unit time. The frequency is the number of rotations per unit time. But there are 2 pi radians in each rotation. So 2 pi times F, this is going to be 2 pi radians per unit time times the number of rotations in that time period. Let's say it's, again, 5 rotations per second. There's going to be 2 pi times 5, 10 pi radians every second for the rotation. So this is equal to the angular velocity, the number of radians per second. So this is the same as omega. Omega is the angular velocity, the number of radians per second. If I have 5 rotations per second, then there are 10 pi radians every second. That's an angular velocity. Well, so omega, not only is it equal 2 pi times the frequency, but it's also going to equal 2 pi divided by the period, right? Frequency is 1 over period, So omega will be 2 pi over the period as well. Okay? So there's a relationship then between the angular frequency and the period, the angular frequency and the rotations per second. It's also a frequency. Okay? Now, let's think about this for a second. My speed going around, right? My speed going around, how many feet per second or inches per second or meters per second, whatever that speed is. I'm not going to go with velocity yet because we don't know a direction. But my speed, that would be the derivative of this with respect to time. Okay, so speed would be the derivative of s with respect to time equals the derivative with respect to time of r theta. Right? But r is a constant. In our cases, we're going to stick with constant radii. We talked about it where the radii change. We did that when we talked about normal and tangential and radial transverse velocities and accelerations in previous lectures. But let's assume that I have a nice circular motion. The radius is constant. That's the derivative of theta with respect to time. So this is r omega. And so my speed, oftentimes called my tangential velocity, is equal to r omega. The other way you can look at this is distance over time. A full circle, right, is 2 pi radians, and then the time for one full rotation is t, but one full rotation in distance is 2 pi r. So I would just multiply this by r, 2 pi over t, that's omega, and so this is equal to omega times r, or r omega. So I get the same thing no matter how we look at it. Right? So that gives me the relationship then between angular velocity and translational or linear speed, tangential speed. Okay, again, we'll look at vectors here next time. All right, if you have any questions on this first part, be sure to leave them in the comments below. Thank you.